Okay, and now we are recording. So, first topic for today. That's weird. You can see the, yeah, okay. So, semantics. So, at a basic level, pages can be indexed just by search terms, right? And this works pretty well if there are very rare terms on mostly text pages. But it doesn't work so well if there are very popular searches, right? Searches that return many millions or even billions of results on pages with a lot of objects. So, remember, Google is working semantically to try to match the user's intent. Tries to figure out what the user is looking for, and it recognizes that it might not be well served by an exact text match. So, indexing can incorporate excuse me, semantics by creating entries for term groups or concepts. Remember, we had the basic idea. Every index entry is part of this key value store, where the key is some index terms, and the value is the set of pages matching that term. So, for example, the terms buy car. Google has a lot of data. It recognizes that somebody who's searching with those terms buy car is probably actually looking to buy a car, right? Rather than looking for a how-to article, how do you go about buying a car, or doing price comparisons, right? So Google, over the last 20 years, they've learned that people who buy car who search for buy car tend to click on links to dealerships as opposed to informational articles. And that kind of factor gets integrated into normal search and can also be displayed separately through the knowledge graph, right? It doesn't work so well with buying cars, although you might say, oh, you're buying a car? Boom, I'm going to give you a set of dealerships close to you. And that's something that could be included in the knowledge graph. Okay. So not everything that I'm doing is showing up on here. This is weird. There we go. All right, let's try to synchronize these again. There we go. Yes.
So, essentially, index filtering is when Google just kind of uses what past users have searched up in a similar topic to give the current user what they want.
Well, sort of. See, there's always this kind of combination of the factors. So, indexing is just matching the terms to the pages, okay? And includes semantic equivalence. And most of this is done not by humans. This is done in an automated way because there are too many terms. So Google might, for example, recognize that buy car is a functional equivalent to car dealerships, because people that are looking to buy a car click on links to car dealerships. Likewise, people that are just looking for car dealerships, they're going to click on a car dealership, right? And it might be equivalent to things like, what else? What else could be an equivalent? I don't know, buy new car. I'm not really creative this morning. You get the idea, though, yeah? So basically, even though these aren't the same terms, buy car and car dealership, in a semantic sense, they're functionally the same because people that search for buy car are clicking on the same kind of results as people who search for car dealerships, yeah? So the indexing process will consider that. But the raw part, matching the terms to the pages. So in this case, they both have the word car in common, so they're going to have a fair number of pages in common. But when Google compares the two, the retrieval process and the ranking process is saying something else. This is indexing just about how pages are stored at this point. All right. Excuse me. So a normal user won't consider more than a few dozen results, typically far fewer, right? Typically, most searches, the user does not leave the first page of search results. So, in most cases, search engines should only deliver a small portion of the matches. And in most cases, very common words like the appear on most pages and should be excluded because, number one, they don't materially differentiate between pages. The results with or without them tend to be practically identical. Number two, they add a lot of extra ranking effort because common words tend to get repeated a lot on pages, so it makes the ranking process a little slower. And last, the index entries would be extremely large because of the very large page counts, right? So think of all the pages in the internet that have the word the. That's crazy. Well, we're going to see what we come up with that. If we just Google the word the, 25 billion results, right? Which really can't be all the pages, but that have it. Anyway, because if we're just getting sports, right? Sports has 20 billion-ish. The has to have way more. Anyway, but yeah, the would be a very large index entry. Even though they have it, they don't really want to have it. So, anyway, quick example. One thing that we can do, suppose I look up the term Chicago Cubs. Okay? Chicago Cubs, I get this stuff. I get some stuff about recent information. I get the knowledge card over here. Get some Twitter stuff, their official website, blah, 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 blah. Okay? If I go to another page and I do the Chicago Cubs, I should get basically the same results, right? But in fact, they're slightly different. For example, if I do the Chicago Cubs, the official website ranks higher, ranks above Twitter for some reason, right? And all I can think of is it's probably an age-related demographic thing, right? Older people or people that are interested in historical stuff about the Cubs, more likely to type in the Chicago Cubs, right? Younger people that have grown up with search engines, probably just going to type in Chicago Cubs. So there may be some kind of age factor that's driving this, right? Young people use Twitter. Your grandparents are probably Twitter. Nah, forget that, okay? Anyway, but the results, basically all the same stuff is there. If we look at this, it's pretty much all there. All the same stuff, just very slightly different order. Anyway. Okay. So the key thing is, yeah, you know, Google will say that they don't really consider super common words like the in the search. But in fact, you can verify that they are just, they are in there and they affect things a tiny bit sometimes. The first time I was doing this in lecture, I was talking about, yeah, and you know, the words don't affect it at all. And then I did Chicago Cubs and the Chicago Cubs, and there were a couple things out of place. I was like, oh shit. But here we are. All right, mostly they don't. They don't affect it much. Other stuff, interesting related articles. Not going to test you about any of these, but you should know what they are because they may show up as answers on exams. And if you don't know what they are, you might inadvertently guess at one of them. So, this talks about MapReduce. Remember MapReduce, the basic process with that is that if Google had a giant set of pages, right? Many pages, looking for matches, term matches. Okay, the essential process, break up batch of pages into many smaller slices, assign each slice to a separate server, process the slices in parallel, combine, and return the results. Right? This kind of parallel operation we've talked about a few different times. Google has a big batch of information to process. Instead of doing it all on one machine, they chop it up into a bunch of slices, distribute one slice per server, return the processed results very quickly. They used to do that with MapReduce, but since they've switched to a newer model called Caffeine. Basically, Caffeine is a, you know, faster, smarter architecture for doing the same kind of stuff. So that's what that is. It's a technique for basically processing in smaller batches, processing it faster, things like that. Semantic search, we know what semantic search is. Basically, searching in terms of meaning instead of on exact text matches. Now, once upon a time, right, everything at Google was exact text matches. Then they started implementing semantic search for a limited set of topics. But eventually, they came up with this new technology called Hummingbird, where they tried to apply semantic search to absolutely everything they do. Okay? And this last one, knowledge graph, we've talked about the knowledge graph in the context of looking for Galileo on Google. Knowledge graph there's a little article about that. So if you want, you can read all those, just get an idea of what they're all about, and then you won't guess on the wrong thing on an exam. Okay, but that's all you need to know. Just, just be enough to recognize what these things are. Okay. So let's talk about the indexing system. So first, the problem in the abstract. So each request, somebody, people show up at Google, they want to run queries for search. So each request goes to a big cloud system, right? Google has its cloud where it has all these servers storing portions of the index. So we know the tasks, but not actually the details of how the hardware is connected. And in fact, we're not really supposed to, because even when Google engineers are designing these systems, they're deliberately designed to be modular in the sense that, there are these different operations. Okay, let's do circles, I guess. Let's do fuzzy cloud. That's fun. Fuzzy cloud. Yay. Okay. So different parts, right, are going to drift in. So what happens? Number one, search terms entered. Number two, semantics. Okay, and I'll add another one. I'll add typos, which you could argue is a sub-branch of semantics, right? Misspelled words, but they have the same meaning, thus they are semantically equivalent. Okay? I'll put those as a link. So we have that. The search terms go to the semantics, and the semantics go to the retrieval process. Okay, so set of terms and equivalents. Okay. So say actual search, alternate text, whatever, misspellings. Okay, so all this is basically their system. Now the search process, right, Google has google.com. It accepts whatever you enter in there. That part is a modular. So however they set up that website doesn't matter. It's just the input, when you put your words in the text box and you hit enter, boom, that all gets sent to the semantic processing unit. Semantic processing unit, the input is a set of search terms. It connects with this, basically the spell checking feature where it says, here's the set of terms that were actually entered, right? So we'll say, again, actual terms. And then the misspelling system will check and say, oh, that could have possibly meant this, right? Like if you type in BGUS software, it's going to say, oh, you probably meant software bugs and kick that back to you. Then the semantic system will pass forward this set of equivalent terms to the retrieval process, right? So it says, here's all the terms, find all the pages that match those, right? Extract them, rank them, retrieval. So all of these portions of the process, they're designed in a modular way. So when I talk about standard interfaces, the standard input to the semantic cloud here, that's just actual search terms. The standard input to the typo system is a set of actual terms. What it kicks back is a set of, right, non-standard terms, right, what we thought you meant. Then the output from the semantic system is a set of equivalent terms. So you have first the actual search, but then any other sets of terms that might be popular and equivalent, and that goes to retrieval. So all these, they're designed as modules. None of these individual clouds need to know exactly how any of these other things work. They just need to provide the information in a standard format and be prepared to receive the returned information in a standard format as well. Okay? All right, so they're designed as modules. That's what we mean. And again, when Google engineers design these systems are so hairy and complex that there's no way ordinary humans can, learn more than a portion of what's going on in one. So they're designed as modules for that reason, to allow humans to continue developing them. So the big design questions are, number one, what tasks are required to actually handle the queries, right? So we broke it up into all those little clouds. Each of those little clouds, of course, has a set of subtasks within it. What's the sequence of the retrieval process? How does that part work? And what are the associated interfaces? That's essentially all the things that Google has to set up to make this process work. All right. So, system architecture. Like Facebook, and basically for the same reasons, Google doesn't serve all its users from one location, right? Key reasons, number one, if there were a traffic surge, if there were a system failure, it would affect everybody instead of, one subset of its users. Number two, they can keep locally relevant data closer to users, right, and make it easier to deliver locally relevant content faster. And last, energy costs, right? You don't think about it in terms of a particular search, but at the scale that Google is doing it, if they have to send all this information over the world, at that scale, yeah, eventually the energy costs and the transmission costs, all that is going to be significant for them. All right. Still, Google could probably handle it at one data center. They could build one giant data center to do all this. In fact, any one of its, average data centers these days, we don't know the exact size. Some might be dinky. But basically a baseline average data center could probably handle the worldwide search traffic from about 10 years ago. Because you look at it, Google has about 15 data centers last I checked, might have a couple more now, and total traffic has gone up by about that much. So there we are. You may have heard of Google's data centers. Again, giant building, right? Thousands of servers, tens of thousands of servers. We don't know a lot about it. These are the pictures I think I brought up before, but here they are if you want to see them again. This is like the one article that I found that had decent pictures of them, but we gotta wait, so whatever. Okay. So, talk about the details of what goes on in one. So, a server cluster. So each data center contains probably tens of thousands of servers. The tasks typically get split into sections and distributed over sets of servers. And this kind of parallel operation keeps everything going fast. So think about it a simple way. For example, all right, suppose this is a map of my whole index. Map of the whole local index portion. Okay, so whatever part of the index I have at this data center, this is it. Now, clearly what I don't want to do is store information that, okay, so I'm going to say, don't want to store information and pages randomly distributed over the servers, right? Why? Why wouldn't I want to? What's that? Sorry, yeah, how specifically is it harder to find? What's the problem? I mean, what's the actual, that's not wrong, but what's the specific technical problem if I have all of my data stored randomly over all the servers? Think of it like a phone book. Yeah, I have to search every server, right? If I store my information randomly over all the servers, Google would need to search every server involve every server in every query, right? Which is going to add processing time, which will add unnecessary processing time. It's going to make things go slow. So, better, much better, group index entries together, especially semantically equivalent ones, right? So that each query only involves a small subset of servers. Now, clearly, there's a balancing act going on here, right? Because on the one hand, if it's a big task, you want to distribute it over many servers so it gets processed quickly, right? If it's a small task, yeah, maybe you can just do it on one machine. So there is some kind of balancing in there. Some kind of happy medium, which basically more servers faster because smaller slices, right? Because smaller slices, but fewer servers means more searches happen in parallel. All right, so there's kind of a trade-off there. I mean, if you were just thinking about the size of the slices, you would put a tiny slice on every server to super maximize speed. But at some point, right, if your file is 2 megs long versus 1 meg long, you're only going to gain like a few microseconds in processing time there. It's not going to be worth the trouble of the fact that every operation involves every server. On the other hand, right, if you do every query entirely on one server, that could take a long time, right? If there's a server entry that involves several 100 million pages, yeah, that's going to be pretty slow to happen on one machine. So again, there's kind of a trade-off in here. It's a bit complicated, and Google doesn't give us all the details. Okay. So basically, the tasks, right, typically split into sections. Like, if, for example, if you have a large set of index pages, you want to rank them, yeah, they're going to try to split that into a bunch of slices. And parallel operation keeps everything going fast. So functionally, it's very similar to a RAID device, right? What's a RAID device? Bunch of hard disks in a single appliance, right? Yeah. So it's basically like that. This module, this server tier, you have a bunch of servers all operating in parallel, just like if you're doing striping in a RAID device, you break up a file into slices and store it on different portions, different hard disks, right? Same kind of thing. There's a reason why I introduced RAID early on. So, same thing. Traffic is handled through a common interface, directed to particular machines, and you can use parallel processing like striping to get everything done faster. Now, right here, this is actually a very nice article on Ars Technica, and not too technical. If you're interested, you can't see it because that's how that shit goes. Okay. Come on. There we go. Okay. Great disk drive in the sky, how web giants store big, and we mean big data. Although it was 7.5 years ago, so data has gotten much bigger since. Okay? It's a very nice readable article about how this stuff works. Okay? And there's several pages. If you're interested in this, if you're an IDS major, might be some good stuff to read. If you're not, if you're finance or accounting, yeah, okay. Read it if you're interested. Okay. But that is one of the articles I especially recommend is all. Okay. Next thing, hierarchical system. So let's assume for a moment that Google keeps a master copy of all data. So for any bit of data, any copy of a page, for example, it keeps one master copy that says this is the original pristine version. Okay? Now, it is unclear. We don't have a lot of detail about how Google manages this. It's unclear if one data center is assigned that role, or for that matter, if Google even maintains master copies as such. Because we've talked about 3 copies are sufficient to do parity checks. If something goes wrong in one, you could say this one is not like these 2 others. So, and these copies don't necessarily have to be in the same data center, right? You could have 3 different copies in different parts of the world, and in that sense, they'd be safer from, things like natural disasters and lightning and stuff like that. So, what we do know is that Google's data centers do have different capacities and content. And we can verify that by looking at where the data is coming from. But it just makes sense in practice. For example, if there's content that's in a non-local language, why would you keep it in the local data center, right? For example, if pages are written in Japanese, you'd probably keep them in a data center near Japan, not a data center in the UK. Okay, anyway, so if a page isn't stored in the local data center though, right, so one thing we can verify, if the data centers have different content, then we know by definition, not all data centers have every page, right? Because if they all had the same stuff, they'd have all the pages. So if the page isn't stored in a local data center, it has to be retrieved from somewhere else. So in that case, the local index contains information about where the query should be forwarded. And if a query becomes popular enough, eventually the local index will get updated to contain that page. So let's talk a moment about how that works. So let's say Google has a bunch of data centers, and I'll use my standard mix. We got London up here, New York, Chicago, I'll call Silicon Valley one, let's do Seattle, and Tokyo. Okay? And these are all data centers. Now, Simple example. They're all going to be connected in a moment. All right. Now let's suppose there's an article. Suppose the LA Dodgers were in the World Series. And they're not, but suppose they were. Yeah, LA Dodgers in World Series. Okay? Pages about that. They're almost certainly going to be stored in this data center, right? Because they're locally very significant knowledge. It is possible that those pages could be also stored, plus here, where baseball is popular, plus here, maybe, New York is playing LA in the in the World Series, and so maybe it appears there. Or maybe it's just there anyway. Seattle, sure. Maybe even here. Okay? Probably not in Tokyo, right? I mean, baseball's popular in demand, but here's the thing. These pages are going to be in English, right? So they're probably not going to store English language pages in Tokyo. They're probably going to probably, at most, Japanese equivalent pages. Okay? At most. Or they might have, articles written by local media in Japanese. Probably not going to have the same article. Right? We understand that? So, suppose then, here's our case. Some U.S. expat in Tokyo, right, searches for LA Dodgers info. Okay? And they find the page. Well, the Tokyo Data Center Index is not going to have any copies of that page. But what it will have is say, oh, you're looking for these things. I'm going to route this request up and over here because I know where that is, right? So the index entry will say, oh, you want that. You got to go to the Silicon Valley Data Center because that's where that page is. So you make the call there. The Silicon Valley Data Center sends the pages back. There you have it. Now, of course, over time, if enough Tokyo users make the same search, it will begin to be stored locally as well, right? Clearly, it is possible to have multiple copies of the pages stored in multiple data centers, right? If there's, suppose, I don't know, somebody, no, I'm just thinking out loud. Suppose there's a major U.S. event, right? Let's say what it is, something good. Let's say friendly aliens visit Earth in Chicago and bring beer. Okay? That is big news. So that is going to be in every data center in the U.S., right? We can agree on that. That is definitely some news. It would appear here, appear here, appear here. It will be everywhere. So it is totally possible for different data centers to have different copies of the same article, same pages. Why? Because it enables all these requests to be served faster. If there's a big bottleneck, right, if everybody on Earth wants to read about aliens bringing beer and what kind of beer they brought, right, you don't want them all to have to go to this one data center. You want to be able to serve those requests locally. Does all that make sense? Okay, so that's like a lot of the architecture problem they deal with. If stuff isn't stored locally, the index entry for that just says, here's where to go to find that. If stuff is stored locally, you can store it right away. And if any request over time can become popular, can be unpopular, can shift between data centers. So maybe, these articles, they're popular for a little while the Dodgers are actually in the World Series, but then they fall away from these other data centers as they stop being popular after the World Series is over. Maybe they stick around in Silicon Valley for a few extra days because, it's local and people are still interested. All right. So, again, if a page isn't stored locally, it has to be retrieved from another data center. So that local index contains information about where to get the query results. And if the query gets popular, eventually that local data center will start holding copies of those pages as well. All right. So Google stores a replica of each page its spiders visited like a duplicate surface web, right? And this is pretty big, so basically making a copy of the internet. So Google, of course, doesn't want to copy the entire index and set of page replicas to every data center because most pages at most data centers would not get many views. It wouldn't be worth the trouble, right? Tremendous storage cost. If, say, Google is keeping, I don't know, 10% of all pages in each data center, they basically need to have their data centers be 10 times as big. That becomes expensive. So localization basically means any particular data center is going to store pages predicted to be of greater local interest. Main things, stuff like local places, local people, language, stuff like that. So for example, if there's an article about the mayor of Chicago, something happens, yeah, that's going to be big news in Chicago. That'll be on all the Chicago data centers. But other data centers around the world, maybe, maybe not. Okay? And when necessary, again, non-local pages can be retrieved from other data centers. Okay. Like Facebook, remember we talked about the long tail popularity problem? So with Haystack, Facebook observed they had this problem where a lot of photos that were even more than a year old were still getting looked at, right? They didn't have this problem where, oh, if once something is a couple pages old, nobody's looking at it very often, so we can just throw it in cold storage and not worry too much about retrieving it. And they found out that, yeah, a fair number of older photos were still getting looked at. So they have to deal with that long tail popularity problem as well. So sure, at any given moment, the majority of searches are for current events, but there's still a substantial minority that are for very old pages. And also for Google, Google experiences perpetual novelty. This is the last year I have a stat on this, but in 2013, Google said that 16% of its searches were unindexed. It was the first time that anybody had made those searches. It might sound crazy, but a lot of it is just going to be different names and different combinations, right? So, for example, in 2013, somebody might have written as a search, why does Professor Lundquist drink so much Pepsi Max? We don't know. But that's probably the first time that query was made, for example. Okay? Once the system starts turning into these natural language schemes, you're going to get a lot more queries like that. Oh, there's one that includes professor. Professor of neurology. Lindquist, different guy. Bummer. All right. Okay. So one thing Google can do can optimize performance by continuously updating and caching popular search results. It knows most of the searches are for things that are trending or otherwise popular, or for popular Wikipedia pages, so it can cache all of those. But the older, less popular pages absolutely can't be ignored for the same reason that Facebook can't ignore them, because even though they're not popular, they come up often enough that Google has to give good performance for them too. Okay. All right, let's talk about, we'll do a couple more slides, then we'll take a break for today. So, when a search query is received and the system has determined that it's going to be handled locally, basic way the task breakdown works. First, Google checks if the search results are already available from prior searches, right? So, we have this basic process. Okay, so, first, check if the search will be handled locally. Okay? Assuming yes, then a bunch of stuff happens, right? So, first, index terms get parsed from the query. So, extract terms, especially semantic units, from the query. Okay? So, for example,